Hello and welcome to Controllerstech. Before we begin, I want to give a big thank you to our Patreon members, David Lutz, Friedrich Boak, and Robert Johnson, for their generous support. You can also support the channel by becoming a member on Patreon. Do check out the link in the description. In the previous video, we saw how to configure an STM32 as a Modbus TCP server, and how a client can request input data from it. I connected 10 switches representing 10 different inputs, and the client was able to read the current state of each switch. Today, in part 2 of the STM32 Modbus TCP series, we will see how to work with coils. The STM32 will still act as a TCP server, and the client will now be able to both read and write coils connected to it. Before we get into it, let's quickly go over what coils are. Coils are single-bit values, meaning each coil can only be either 0 or 1. They can be read or written by the Modbus client, but they can also be accessed by external sources. Now, here you can see the function codes used for coil operations. Function code 1 is used to read coil data. Using this same function code, the client can request the status of either a single coil or multiple coils at once. Function code 5 is used to write to a single coil, and function code 15 is used when you want to write to multiple coils at the same time. In this video, I will show how a Modbus client can read and write coils. I will also show how coils can be accessed from an external source, in this case, a Web UI built using Mongoose. The Web UI will display the current status of each coil, and we will be able to change any of them individually. I will continue using the Mongoose networking library for this video as well. Mongoose is an open-source networking library designed for embedded systems and IoT devices. It is written in C and is very lightweight, which makes it a perfect fit for microcontrollers like the STM32 where memory is limited. What makes Mongoose really useful is that it supports a wide range of network protocols, including HTTP, HTTPS, WebSocket, MQTT, and of course, Modbus TCP. It handles all the low-level networking details in the background, so you can focus on writing your actual application logic instead of dealing with complex networking code. Mongoose is also trusted by some big names in the industry. Companies like Siemens, Texas Instruments, Renesas, Samsung, and Bosch have used Mongoose in their products, which speaks a lot about how reliable and production-ready this library is. For this series, Mongoose is the perfect choice, because it gives us a simple and clean way to set up a Modbus server on the STM32, without writing everything from scratch. Now that we understand what Mongoose is, and why we are using it for this series, let's go to the Web UI wizard to create our project. I am going to continue with the previous project, which was about reading inputs. So the first thing I will do is load the wizard configuration from that project. You can find the wizard configuration inside the Mongoose folder itself. Alright, you can see the wizard has loaded with the previous configuration. Now go to Settings, then select Directory, and choose the folder of the previous project. I am going to edit that project directly instead of creating a new one, because this entire series will be covered within a single project. You can see that the target architecture and build environment have been updated to use the Nucleo H755 development board, with Cube IDE as the environment. Now we only need to make a few small changes in the wizard. Since we are moving from inputs to coils, let's start with the REST API section. Go ahead and rename the API endpoint to coils. Unlike inputs, coils can be both read and written from the Web UI as well as from the Modbus client. So we will remove the read-only attribute that we had set earlier for the inputs. I will leave the attribute level as it is, so each coil will be accessed using coils.level. Now go back to the page container and make a few changes to match our new API endpoint. First, change the API variable of the container to coils. Then in the text field, replace the word input with coil. The numbering will still start from 1, so we will have coils ranging from coil 1 to coil 10. Also set the toggle button API variable to coils.level. That is all the changes we need to make in the wizard. We basically just replaced inputs with coils, and since coils support both read and write, the Web UI and the Modbus client will now be able to do both. Generate the project again, so the Mongoose files can be updated in the previous project. The project has been generated, so now let's import it into Cube IDE. Alright, the import was successful. Let's quickly verify that our changes are reflected correctly. Open the Mongoose glue.c file, and you can see that the functions now reference coils instead of inputs. This means that our changes have been applied correctly. Now let's open the main file. I am going to comment out all the input-related code that we wrote in the previous video, and instead we will define new functions for the coils. I am also creating separate indicators for the inputs and coils, since we are using the same project throughout the series, and we need to keep things organized. Before we proceed with the code, we need to make a few changes in the CubeMX configuration. Open the project in CubeMX. The only change we need to make here is to configure the pins as output instead of input, and rename them as coil 1, coil 2, and so on. Everything else stays the same as we set it up in the previous video. Alright, I have renamed all the pins from inputs to coils, and that is all the configuration we need. Now click Generate Code to update the project. Before we move on to the code, let's take a quick look at the wiring. I have connected 10 LEDs to the STM32, which is acting as the Modbus TCP server. These LEDs are connected to the same pins where the switches were connected in the previous video, so instead of switches we now have LEDs. The cathodes of all the LEDs are connected together, and then connected to ground through a 330 ohm resistor. This limits the current through the LEDs, and prevents them from burning out. Alright, now let's get into the code. First, we will copy the Mongoose handler from the glue file, and paste it inside the main file. We also need to rename the function from glue Modbus handler to my Modbus handler, because the original function is already defined in the glue file, and we do not want a conflict. Now let's delete the read and write coil definitions from inside this handler, since we will be writing those functions ourselves. Let me explain how this works. The handler checks which function code is being requested by the client. These function codes are defined in the Mongoose header file, and you can see all of them listed there. If the client wants to read coils, the handler calls the read coil function, and passes the return value into the requested bits array. If the client wants to write multiple coils, the handler calls the write coil function, which takes two parameters, the address of the coil to update, and the value to write, which is either true or false. So we need to write both of these functions ourselves. Now, as I mentioned earlier, coils can be modified from multiple sources, by the Modbus client, or from an external source like the Web UI in our case. To keep track of the current state of each coil, we will define a small database. I am calling it coils data, and it is an array of 2 bytes. The reason we only need 2 bytes is that each coil occupies just 1 bit in memory, and since we have 10 coils, 2 bytes are enough to hold all of them. The read coil function will read data from this database, and the write coil function will update it. Let's write the read coil function first. Inside it, we define a variable called start byte, which figures out which byte a particular coil belongs to. For example, if the client requests coil 12, that coil sits in the byte 1, so start byte calculates that position. We also define another variable called bit position, which figures out exactly which bit inside that byte is being requested. For example, coil 12 is in byte 1, at bit position 4. Once we know the exact byte and bit, we simply fetch that value from the database and return it. Now let's write the write coil function. It also takes two parameters, the coil address and the value to write. Just like before, we calculate the start byte and bit position to find exactly which coil needs to be updated. Then, depending on the value passed in, we set that particular bit to 1 if the value is true, or 0 if it is false. Now, at this point the database is being updated, but not the LEDs. That is because we have only updated the database so far, and have not modified the physical pins. To actually control the LEDs, we need to write to the output pins as well. To do that, we will define a structure array similar to what we did for the inputs in the previous video, but this time we will call it coils, and it will hold the references to each coil pin. Alright, the renaming is done and we now have the array set up for all 10 coils. Now, after the database has been modified, we simply call the HAL-GPIO write pin function, to update the state of that particular physical pin. The port and pin parameters will be passed from the structure array, and the pin state is already available from the function parameter. Our Modbus handler is almost ready. I said almost, because we have the functions to handle reading and writing multiple coils, but we still need to handle one more function code, which is writing a single coil. So I will add one more else if condition for that case. When writing a single coil, the client only sends one value, so we do not need for loop here. Inside the write coil function call, we simply pass the coil address and the first element of the bits array, since there is only one coil being written. Now the handler is complete. We have everything we need to handle reading and writing coils over Modbus. Next, we will also write the Web UI related functions. We already covered the general idea of this in the previous video, so this should feel familiar. First, we need to increase the number of elements in the coils structure to 10, since we are working with 10 coils. We also need to rename the coils structure here, because the original name is already being used in the glue file and we want to avoid any conflicts. Let me update that name everywhere it is used in the other functions as well. Alright, now let's look at the glue getCoils function. This function is called by the Web UI whenever it wants to fetch the current status of the coils. This function first calculates the requested array size and performs a size check. We will leave that part as it is. Our main work starts after that. Once the size check passes, it fetches the coil status from the myCoils array. But before that can happen, we need to make sure that array actually holds the current states of the coils. To do that, we will add a for loop that reads the current value of each input using our read coil function, and stores it into the myCoils array. We are reusing the read coil function here, because it keeps the code clean and consistent. That is all we need to do in the get function. Now let's look at the glue setCoils function. This one is called by the Web UI when the user makes a change on the interface, and wants to update the state of a coil. Just like the get function, it first checks the requested array size and then stores the incoming data from the Web UI into the myCoils array. Once that array has been updated, we need to push those changes to the database and to the physical pins as well. To do that, we simply call the write coil function for each element in the myCoils array, since that function is already set up to handle both the database update and the pin output. That is all the changes we need to make here. Now let's go to the main function, where we need to register our custom handlers. The custom Modbus handler is already assigned, so no changes are needed there. We just need to define the custom getter and setter functions for the coils, so let's update the setHTTP handlers function to include the functions myGetCoils and mySetCoils. The Mongoose WebSocket reporter will then call these functions every 200 milliseconds to keep the Web UI updated with the latest coil states. It looks like there is a build error. That is because I forgot to rename the getter and setter functions, they were still referencing the default glue names. Let me fix that. Alright, the project now builds without any errors. Let's flash it to the board. Also open the serial console to view the logs from the Mongoose library. You can see that the library has been initialized, but the network is showing as down, because I have not enabled Ethernet yet. Let me enable it, and here you can see, we have an IP address now. Let me copy the IP address and paste it into the browser. You can see the Web UI has loaded. I forgot to change the container name from discrete inputs to coils, but I will fix that in the final code. You can see all 10 coils listed here. Now let's open the Modbus client to do some testing. Enter the IP address of the server and the port, which is still 502. Let's connect. Alright, we are connected. Now enter the starting address of the first coil, which is 1, and request the data for 10 coils. The function code will be 1, which is for reading coil status. Let's send this request to the server. You can see the server has responded, and all 10 coils are reporting 0. That is expected, since all coils are set to 0 by default. Now let's take a closer look at the request sent by the client. The first 2 bytes are the transaction identifier, which are 00 and 01. This is a unique ID that the client generates for each transaction, and since this is the first one, the ID is 1. The next 2 bytes are 00 and 00, which is the fixed protocol identifier for Modbus. After that, the next 2 bytes are the length field, which tells us how many bytes will follow after it. The 6 bytes of length includes 1 byte for the unit identifier, which is 0A, this is the slave ID we set in the Modbus client. Then comes 1 byte for the function code, which is 01 for reading coils. The next 2 bytes are the starting address, which is 0 since we are reading from the very first coil. And the last 2 bytes represent the number of coils being requested, which is 10, so the value is 00 and 0A. Now let's look at the response from the server. The first 2 bytes are the transaction ID, which matches what the client sent. The next 2 bytes are again 0, the fixed Modbus identifier. Then comes the length field, indicating that 5 bytes follow. Those 5 bytes include 1 byte for the unit ID, 1 byte for the function code, 1 byte indicating how many data bytes are being sent, which is 2, and finally the 2 actual data bytes, both of which are 0. Now let's write some data to the coils. We need to open a separate write window for that, start from the first coil, and write to 10 coils. You can see the function code has automatically changed to 15, which is for writing multiple coils. I am going to set coils 1, 3, 5, 7, and 9 to 1, while the rest stay at 0. Also take a look at the STM32 board in the bottom left corner, you can see 10 LEDs connected to it. Let's send the write request and see what happens. You can see that LEDs 1, 3, 5, 7, and 9 have turned on. Some may have minor wiring issues, but you can also confirm the same state on the Web UI, where the corresponding toggles have switched on. So we can successfully modify coils from the Modbus client. Now let's try doing the same from the Web UI. I will turn coil 3 off, and you can see the third LED has turned off. Now I will turn off coil 9 as well. So now only coils 1, 5, and 7 are on. Let's send a read request again. You can see that bits 1, 5, and 7 are set to 1 and the rest are 0, which is exactly how we configured them from the Web UI. Now, we do not always have to start reading or writing from coil 1. For example, I can request data starting from coil 5. Let's request 4 coils starting from coil 5. The response shows coil 5 is 1, coil 6 is 0, and coil 7 is 1. That matches the current coil's status. Let me also turn on coils 8, 9, and 10, and then request 6 coils, starting from coil 5. The response shows coils 5, 7, 8, 9, and 10 are all 1, while coil 6 in the middle is 0. So we can read from any starting position, not just from the beginning. We can also write to coils, starting from any position. For example, I will write 6 coils starting from coil 5, and I only want to turn on coils 6 and 8 while the rest are off. You can see the changes reflected both in the Web UI and on the LEDs connected to the STM32. We can also write a single coil using function code 5. For example, I will select coil 6 and set it to 0. You can see coil 6 has turned off. So everything is working as expected. We are able to read and write both single and multiple coils, from both the Modbus client and the Web UI. Coils are single-bit values that can be updated from anywhere, which is exactly what we demonstrated here. That wraps up this video. In the next video, we will continue with the STM32 Modbus TCP server, and this time the client will read and write holding registers. I hope you found this video helpful. You can download the project from the article linked in the description below. Leave comments in case of any doubt. Keep watching and have a nice day ahead.